I'm given two lists. y_true contains the actual class labels 0 or 1, and y_prob contains the model's predicted probabilities for the positive class 1. For example, the first data point has a true label of 0 and a predicted probability of 0.1. This shows that the model predicted a low probability of belonging to class 1. Let's calculate the Brier score. The formula is brierscoreloss equals 1 n asterisk sigma y_i y_prob_i squared. This means I take each data point, find the squared difference between its true label y_i and predicted probability y_prob_i, sum all these squared differences, and finally divide by the total number of data points, n. It's a straightforward calculation that measures prediction accuracy. The formula is a mathematical expression of the Brier score loss. Sigma represents summation. The formula sums up the squared differences between each true label, y_i, and predicted probability, y_prob_i, for all data points. I then divide the sum by the total number of data points, n, to get the average squared difference. A lower score means better predictions. I'll use the Brier_score_loss function from the scikit-learn library in Python to calculate the Brier score more efficiently. This function takes the y_true and y_prob lists as input and directly outputs the Brier score loss. It's a time saver, making my life easier. The Brier_score_loss function will give me a single number representing the Brier score for the dataset. This number represents the average squared difference between the actual and predicted probabilities. A smaller value indicates a better performing model. Let's see how well our model did. This is the final output of the Brier score calculation. I expect a value between 0 and 1, where 0 indicates perfect prediction and higher values indicate poorer performance. The lower the better. I'm given the true labels, y_true, and the predicted probabilities, y_prob, for a binary classification model. The y_true values represent whether an event actually happened, 1, or not, 0. The y_prob values are the model's estimates of the probability of the event happening. This is a list of the actual outcomes, 0 representing a negative outcome and 1 a positive outcome. For example, the first case was negative, the next two were positive, and so on. This shows the model's predictions of the probability of a positive outcome for each case. The model is pretty confident about the second and third cases being positive, 0.8 and 0.9 probability, less so about the last one, 0.6 probability, and not very confident about the first and fourth cases being positive, 0.1 and 0.2 probability. I'll manually compute the Brier score to check the automatic calculation, although the automatic method is preferred because it's less prone to error. I calculate the squared difference between each true label, y_i, and its corresponding predicted probability, y_prob_i. This measures how far off the prediction was from the reality. For instance, 0 to 0.1 squared equals 0.01 means the model predicted a 0.1 probability of a positive outcome when the actual outcome was negative. I'm summing all the squared differences calculated in the previous step. This gives me a total error across all predictions. I'll divide the sum of the squared differences by the total number of predictions, 5 in this case, taking an average error. This is the final Brier score, representing the average squared prediction error. A lower score indicates better performance. I use the Brier_score_loss function from the scikit-learn library, a popular machine learning library in Python, for a more efficient and reliable calculation. This avoids manual calculations, which are more prone to errors. This is how I call the function, passing the true labels and predicted probabilities as arguments. The function returns the same Brier score as my manual calculation, confirming the result. Good job, Vamsi. The Brier score, 0.052, is indeed less than 0.2, indicating relatively good model performance. This shows the actual, or TRUE, Classifications of 5 data points. Each O represents a negative classification, and each one represents a positive classification. For example, the first data point was actually negative. These are the model's predictions. Each number is the probability of the data point being positive. For example, the model assigns a probability of 0.1 to the first data point being positive, meaning it's 90% confident that it is actually negative. So you see, we have probabilities instead of definite O or 1 classifications like in y_true . I'm presenting a small dataset containing true labels, y_true , and corresponding predicted probabilities, y_prob . This is the essential input for calculating the Brier score. It's crucial to understand that the Brier score evaluates how well a model estimates probabilities instead of just predicting class labels. I'll calculate the Brier score, a metric assessing the accuracy of probabilistic predictions. The lower the Brier score, the better the model's performance. A perfect model has a Brier score of 0. I add up all the squared differences, each, y_i, y_prob_i, squared. This process accumulates the errors produced by the model, quantifying the discrepancies between the true labels and the predicted probabilities. This is the final Brier score loss, calculated by averaging the sum of squared differences over all data points. This score tells us about the overall accuracy of the model in terms of its probability predictions. The lower the number, the better the model's predictions. This section presents various statements about the calculated Brier score loss, allowing you to evaluate your understanding of the result and the Brier score's interpretation. Given our calculated Brier score loss of 0.052, I state that this statement is true. Our calculated value is less than 0.2. I have the true labels, 0 or 1 representing negative or positive class respectively, and predicted probabilities for a binary classification model. The true labels are y_true equals 0, 1, 1, 0, 1, and the corresponding predicted probabilities are y_prob equals 0.1, 0.8, 0.9, 0.2, 0.6, . Each pair represents a single data point. For example, the first pair, 0, 0.1, means the true label was 0 and the model predicted a 0.1 probability of it being a 1. This is the formula for the Brier score loss. Let me break it down. N is the total number of predictions. Sigma means summation, wheel sum over all the data points. For each point, I subtract the predicted probability, y_prob_i, from the true label, y_i, square the difference, and then add it all up. Finally, I divide the sum by n. The result is the Brier score loss, which measures how far off the model's probability predictions are from the actual outcomes. A lower score means better performance. Sklearn is a popular Python library for machine learning. Here, I use its built-in Brier_score_loss function to calculate the Brier score. I feed it the true labels, y_true, and the predicted probabilities, y_prob. This function does all the calculation for me, so it's much more efficient than doing it manually. After doing the calculation, either manually or with Sklearn, I found that the Brier score loss is less than 0.2. This indicates that the model's predictions are reasonably accurate. This is the process of calculating how well a classification model's probability predictions match the actual outcomes. A lower Brier score means better predictions. I use either the formula to do the math step by step, or I leverage the Sklearn's efficient function. This is a multiple-choice question testing your understanding of the Brier score. Each option presents a different claim about the Brier score value that I have calculated. The goal is to select the option that accurately reflects the calculated Brier score. This statement claims that the Brier score is exactly 0. A score of 0 means perfect predictions. However, since my model is not perfect, this option is incorrect. This option states the Brier score is less than 0.2. Given my calculation, this is a correct statement. This option claims the Breyer score is greater than 0.2. Since my calculation shows otherwise, this is false. This option says the Breyer score is greater than or equal to 0. The Breyer score is always non-negative because it's based on squared differences. So this statement is true, but is not very informative about the model's performance. I'm given the true labels, what actually happened, and the model's predicted probabilities. YTRUE shows the actual outcomes, 0 or 1, and YPROB represents the model's confidence that the outcome is 1. For example, the first data point shows a true label of 0 and a predicted probability of 0.1, indicating the model is relatively certain the outcome is 0. I calculate the squared difference between each true label, yi, and its corresponding predicted probability, YPROBI. I'm essentially measuring how far off the model's predictions are from the actual outcomes. The more significant the difference, the larger the squared value and therefore greater the penalty in Breyer score. I add up all those squared differences from the previous step. This gives me a total measure of the model's overall error. It's like accumulating all the individual prediction errors to get a big picture of how well or poorly the model performs. To get an average error across all predictions, I divide the sum of squared differences by the total number of data points, which is 5 in this case. This averaging step gives a single number representing the average error per prediction. This is the final Breyer score loss, a single number representing the average squared difference between the true labels and the predicted probabilities. A lower Breyer score loss is better and indicates a more accurate prediction model. Here, I've obtained a Breyer score loss of 0.052, representing the average squared error of prediction by the model. A lower score means the model's doing a pretty good job. I'm given the true labels, 0 or 1 representing negative or positive class respectively, and the model's predicted probabilities for the positive class. These are the inputs for calculating the Breyer score. Specifically, y_true shows the actual class, and y_prob shows the model's confidence that each data point belongs to the positive class. This array holds the actual class labels for 5 data points. For example, the first data point is actually in the negative class, 0, the second and third are positive, 1, the fourth is negative, and the fifth is positive. This array shows the model's predicted probabilities for each data point being in the positive class. For example, the model predicts a 10% chance that the first data point is positive, an 80% chance for the second, and so on. I'll show you how to manually calculate the Breyer score. We'll take each data point and calculate the squared difference between the true label and the predicted probability. Then, I'll sum those squared differences and divide by the total number of data points to get the average. This gives us the Breyer score loss. This is the formula for the Breyer score loss. Let's break it down. N is the total number of predictions. Asterisk sigma asterisk means summation. We'll sum up the results for each data point. Asterisk, YY_prob. Squared calculates the squared difference between each true label, Y asterisk, and its corresponding predicted probability, Y_prob asterisk. The whole thing is then divided by N to get an average loss. I'm importing the Breyer_score_loss function from the scikit-learn library. This function is a more efficient way to calculate the Breyer score than doing it manually. The Breyer score loss will be less than 0.2, based on both the manual calculation and the scikit-learn function. This is the question we need to answer based on the Breyer score. The question asks which statements about the calculated Breyer score are true. This statement is false. A Breyer score of 0.0 means perfect prediction. Our model isn't perfect. This statement is true. Our calculations show the Breyer score to be less than 0.2. This statement is false. The Breyer score is less than 0.2. This statement is true but not useful. The Breyer score is always non-negative, so this doesn't really tell us anything about the model's performance.